Thank you for watching this video lecture, and apologies again that I cannot make it at our timetabled lecture slot. This is the first lecture in the series of aquatic chemistry, an important branch of chemistry, as water is always considered as a key player in the chemical change in natural environment. For example, the reactions leading to ocean acidification and concrete carbonation. Such systems are very complex indeed, and in addition to water, these systems contain mineral phase and gas phase, as we can see here. Let's take the ocean acidification as an example. It is caused by the uptake of carbon dioxide from the atmosphere. To achieve chemical equilibrium, the higher the carbon dioxide partial pressure in the atmosphere, the higher the concentration of carbonic acid in water, and the higher the concentration of hydrogen ion in water. Compared with the time before Industrial Revolution, the hydrogen ion concentration has increased around 30% in the world's oceans. Other chemical reactions are triggered by this and result in a net decrease in the amount of carbonate ion available. This makes it more difficult for marine calcifying organisms to form biogenic calcium carbonate, and such structures become vulnerable to dissolution. You may have already heard that the ocean acidification has been called the evil twin of global warming and the other carbon dioxide problem, just because of this. For our course, we will mainly use carbonation of concrete to help us explore these systems. The corrosion of steel reinforcement remains at the heart of concrete failure. We are interested in concrete carbonation is because it triggers the corrosion of steel reinforcement. This image shows an international standard method to determine the carbonation depth of concrete by measuring its pH, which we will discuss in more detail in lecture 12. Just to say, the current lecture is lecture 10. The process of concrete carbonation relies upon the presence of moisture, which is water, and the action of environmental force, in this case carbon dioxide. As soon as the concrete is exposed to the air, the process of carbonation can begin. Carbon dioxide slowly penetrates the surface of concrete, which it reacts with moisture and calcium hydroxide to form calcium carbonate. The process of carbonation reduces the concentration of hydroxide ion, which are produced by the dissolution of calcium hydroxide, and therefore lowers the pH of concrete to less than 9, which is the level the reinforcement can be corroded. As the steel reinforcement rests and expands in volume, it places force on the concrete, which cracks finally and causes structure failure. As we are talking about carbonation of concrete, I just would like to show you another cycle. We have learned carbon cycle, nitrogen cycle, and water cycle. Here's another cycle, lime cycle. Here. The cement manufacturing, concrete making, and the carbonation of concrete belongs to the lime cycle, another big cycle modified by our activity. We can see here limestone here is the most stable form, and therefore it is abundant in nature. Okay, let's get back to the main contents of this lecture. In this lecture, we're going to talk about two equilibrium constants, ionic product of water and acid dissociation constant. Apart from this, we will also talk about pH, we need to know pH. As we can see from the previous slides, pH is an important monitoring parameter for the reinforced structure. Before we dive directly into today's topic, let's recap what we have learned about Gibbs free energy, dynamic equilibrium, and equilibrium constant. We now know that the equilibrium constant means a state of balance. The concentration of reactant and products do not change over time once equilibrium has been established. Although the concentration of reactant and products remain constant, both the forward and reverse reaction are still proceeding. As the concentration of reactants and products remain the same, the forward and reverse reactions must occur at the same rate, as shown here. Chemical equilibrium is therefore stable and dynamic in nature. About the equilibrium position of any reaction or the extent of reaction or how far a reaction can proceed depends on two factors. One is the standard Gibbs free energy, and the other is reaction quotient. First factor, standard Gibbs free energy, can be calculated from tabulated figures and therefore very straightforward. There is one thing to note, that, however, that is the standard Gibbs free energy is the free energy at 25 degrees Celsius, which is defined as standard condition. The Gibbs free energy is slightly different at any other temperature levels. We're not going to talk about this in more detail as it is beyond the scope of this course. However, we need to know this point. Equilibrium constant, the capital K, is a fixed, this equilibrium constant, the capital K, is a fixed value at any fixed temperature for any given reactions, and it can be calculated from the standard Gibbs free energy directly. If we imagine the standard Gibbs free energy can control the seesaw on this slide, we know the seesaw will turn in clockwise direction if the standard Gibbs free energy is a negative value, as shown on the left-hand side of the picture. If we imagine the constant K now control the seesaw, what kind of value K should have in order to turn it clockwise? I will leave this question to you. We will see this equilibrium constant more often than the standard Gibbs free energy in this course, as K can be used to compare directly with reaction quotient Q, which is part of the other term in the equation to determine the direction of reaction under any conditions, rather than 1 mole per liter for solution, 1 atmospheric pressure for gas, etc. For a mixture of reactants and products, after we know the concentration of each of them, we can calculate the corresponding reaction quotient Q. If the value of Q is less than K, then the reaction will proceed forward. Please revise lecture 8 if you are not familiar with what I just said. This slide shows that for any given chemical reaction, there is a relationship between the concentration of the products and reactants at equilibrium. Please note the concentrations in this equilibrium constant equation should be concentrations at equilibrium. From this equation, we can see that while the equilibrium constant is fixed, there are an infinite possibilities of combination of equilibrium concentrations. I have provided an example on this slide to explain this point. For all of these equilibrium combinations, if we plug the values into the equilibrium constant equation, we get 100. However, they are all different. In the third scenario, it might be hard to think this reaction favors the product as the concentration of the product is much lower than that of one reactant, but due to the extremely low concentration of another reactant, the system achieves equilibrium. We're going to see more of this in this series of lectures. So, first new topic of this lecture, ionic product water. Water, as we have learned, is a covalent substance, but even in the most pure sample of water, there is always a small fraction, a small concentration of hydrogen ion and hydroxide ion. These ions are a result of self-ionization, as shown in the title. Here we need to understand a concept about how water can dissociate or ionize. We now know the covalent bond of hydrogen and oxygen is a polar covalent bond, as oxygen atoms are electron greedy, and therefore the electronegativity of oxygen is higher than that of hydrogen. Because of this, the oxygen end of the water molecule has a fractional negative charge, and the other end has a positive charge. Negative and positive charge attract each other, so different molecules are associated with each other through hydrogen bonding. We know liquid water molecules are in continuous motion. What can happen when water molecule collide is that the oxygen atom of one water molecule can actually grab the hydrogen of another water molecule because it can attract hydrogen to itself so strongly. So this one now becomes H3O+. It is hydronium ion. Most of the time we use hydrogen ion to replace this H3O+ because it is much simpler. Although we need to know this H3O+ actually accurately reflect the real ionic structure of the cation. The water molecule that has lost the hydrogen proton now become OH- hydroxide ion. So liquid water can separate into hydrogen ion and hydroxide ion. In any body of water, only a very small percentage of these water molecules are actually ionized. But once ionized, the ions may recombine with each other. But in the meantime, some other molecules are ionized. This is about dynamic equilibrium, so this is a reversible reaction. As a reversible reaction, the self-ionization of water has an equilibrium constant, as shown here, 1.8 times 10 to the minus 16. This is determined experimentally. These equilibrium constant equations provide a relationship between the products and the reactant, as shown here. The brackets denote the concentration of the species in units of mole per liter, the molar concentration. There's a few things we can say about this equation. For example, let's look at the denominator, the molar concentration of water. It can be regarded as a constant, 55.56 mole per liter, as long as the concentration of solutes are not very high. How can we get this value, 55.56? You can pause this presentation now for a minute and think about it. Okay, we know two facts. One, the mass of 1 liter of water is 1000 gram. Two, the molar mass of water is 18 gram per mole. So the molar concentration of water equals 1000 milligram per liter divided by 18 gram per mole, which is this 56 mole per liter. So we can see we actually have two constants in this equation, which can certainly be combined into one. So we get the second equation on this slide. The ionic product of water, Kw, equals the molar concentration of hydrogen ions times the molar concentration of hydroxide ions, which equals 10 to the minus 14, a very nice number at 25 degrees Celsius. The subscript W in Kw stands for water. There are two things we can discuss about this equation. First, this 10 to the minus 14 is the constant for 25 degrees Celsius. For any given reaction, the Gibbs free energy change and the equilibrium constant change slightly with temperature, as I briefly mentioned at the beginning of this presentation. Only by pure luck, the constant Kw, the ionic product of water, has a nice number of 10 to the minus 14. As the concentration of hydrogen ion equals that of hydroxide ion in pure water, so each of them has a concentration of 10 to minus 7, which give a pH of 7 for pure water. At any other temperature, the Kw, the ionic product of water, and associated pure water pH is not so neat, as we can see from this table. The other point is, although Kw changes with temperature, however, at any given temperature, for example, the temperature we usually use 25 degrees C, the ionic product of water is a fixed number, no matter if the concentration of hydroxide ion is equal to the concentration of hydrogen ion. Let's repeat it again. As the ionic product of water is an equilibrium constant, so it is a fixed number at any given temperature. In our course, we only deal with the temperature for standard conditions, which is 25 degrees Celsius. So, the ionic product of water is the first equilibrium constant we have met so far. Let's compare it with the general equilibrium constant we have discussed in Lecture 8. We know for any given specific reaction, we can derive the equilibrium constant reaction equation in question according to this general equation here. The only extra point we need to be aware of for self-ionization of water is this equation is simplified as the concentration of water is a constant. The modified equilibrium constant in this case is called ionic product of water, Kw. The self-ionization of water is an equilibrium process, and the position of this equilibrium lies very much to the left, because the value of Kw is very, very small, and therefore the concentration of hydroxide ion and hydrogen ion is extremely small in pure water as well. Now, let's move on to the next topic, pH. We are interested in pH as it is important in both chemistry, such as pH of concrete, and biology, for example, the pH of blood. Do you know the pH of our blood? The normal blood pH is tightly regulated between, I think, 7.35 to 7.45. You can see it has to be very accurate, to decimal place accuracy indeed. Below and above this range means symptoms and disease. If blood pH moves to, if my memory is right, if blood pH moves to below 6.8 or above 7.8, our body will stop functioning and die. So our body is much more demanding than concrete. About pH, first of all, let's fiddle with the ionic product water. It is a constant at any given temperature, 10 to the minus 14 at 25 degrees C. In pure water, the hydrogen ion concentration equals hydroxide ion concentration, which is 10 to the minus 7. But if we introduce either extra hydroxide hydrogen ion or hydroxide ion into the system, their concentration will be different, but they still have direct relationship through this ionic product water. So if we know the concentration of hydroxide ion, we can calculate the concentration of hydrogen ion and vice versa. If in a solution the hydrogen ion concentration is greater than the hydroxide ion concentration, then we call this solution acidic solution. If hydroxide ion concentration is greater than hydrogen ion concentration, then we call it basic or alkali solution. The compound that can denote hydrogen ion into the solution are acid. By doing so, it can increase the concentration of hydroxide of the hydrogen ion in water. A base, on the contrary, can release hydroxide ion. Acid and base chemistry here is a particular form of aqueous equilibrium chemistry and is important in both chemistry and biology, as we already know. One thing I need to point out is acid and base chemistry is different from many other reactions taking place in water. This is because water itself is made of hydrogen ion and hydroxide ion in some sense. So, when we introduce some acid or base into the water, the solvent water itself will become an active participant in the process of finding the equilibrium position for hydrogen ions and hydroxide ions. For example, when an acid is added to the pure water, this means the hydrogen ions are introduced into the pure water. This action will push the reaction of self-ionization of water backwards in order to reach a new equilibrium position where the products of hydrogen ion concentration and hydroxide ion concentration is still 10 to the minus 14. When the new equilibrium position is reached, the relative concentration of these ions are unequal, and the concentration of hydroxide ions should be a very, very small number. As we can see, the concentrations of these two ions are usually very small. When we are dealing with very small numbers, it is convenient to use logarithm. So the pH is introduced as the measure of the hydrogen ion concentration. pH here is the negative of the logarithm to base 10 of the hydrogen ion concentration. A negative sign is put in front of the log function as we want the value of pH to be positive. So in pH, the little p stands for the negative of the logarithm to base 10, and the capital H stands for the hydrogen ion concentration. Once we know the pH level of a solution using pH meter, we certainly can calculate both the hydrogen ion concentration using this equation and the hydroxide ion concentration of the solution using ionic product water. The figure on this slide shows the pH scale and the pH of different solutions we are familiar with. By using pH scale, aqueous hydrogen ion concentration that may differ by 100 milli are converted into numbers on a scale which runs from just 0 to 14. Now we can see why I take the logarithm just for convenience. Rather than having to say a hydrogen ion concentration is equal to, for example, 72 times 10 to the minus 5, we can simply say pH equals 4.14, just because it is really convenient to use pH rather than the real hydrogen ion concentration in this case. Also, we can see from this figure, pure water has a pH of 7 at 25 degrees C. Again, it is important to realize that there is nothing magic about 7. It just happens like that at room temperature. The ionic product water is nearly exactly a perfect factor of 10 at 25 degrees C. So the math works out a very nice round number, 7. Although pH is introduced for convenience, the unexpected issue is that the use of logarithm makes the mathematics more difficult for some of us. So please remember 2 points. One, the pH scale is inverse. So the pH decrease means the increase of the hydrogen ion concentration. And the second point is the pH scale is not linear. When the pH changes by 1 unit, the hydrogen ion concentration changes by a factor of 10, as shown in the 2 figures at the bottom. Now let's discuss a bit more about acid, the chemicals which can donate hydrogen ion. For some acid, like the hydrochloric acid, HCl, it can dissociate or separate or ionized into hydrogen ion and chloride ion completely in water. We call this type of acid strong acid. We know a solution with low pH or high hydrogen ion concentration is corrosive. It can destroy or damage other substances with which it comes into contact. So the concentrated strong acid solutions are corrosive, and therefore in the laboratory we must handle them with caution. There are another type of acid. They also donate hydrogen ion when it dissolves in water. However, their dissociation does not proceed as completely as strong acid. Here the HA is not the formula of any particular weak acid. It only denotes weak acids in general. The dissociation or ionization of weak acid is not as complete as the strong acid, as we can see here. But on the other hand, their dissociation can proceed to a greater extent than the ionization of water, and therefore they do introduce hydrogen ion into the water. However, the vast majority of acid molecules are still stay as molecules, rather than ionized to cation and ionize. We call this type of acid weak acids, as they are weak in donating hydrogen ion automatically. So if we introduce similar amount of a strong acid and weak acid into water, for example, 1 molar per liter, we will see that weak acid solution will have much lower hydrogen ion concentration and much higher pH level. As the weak acid solution has lower hydrogen ion concentration, so it is much safer to handle, and we even eat or drink many of them, such as vinegar. I provide more weak acid examples on these slides, so we can see we actually eat lots of weak acids. In this series, in this chemical course, we will focus on two weak acids. One is the acid in vinegar, and the other is carbonic acid, the acid produced when carbon dioxide dissolves in water. Before I start to talk more about weak acid and its partial dissociation, I would like to introduce an important type of reaction, neutralization. This reaction is very useful for environmental protection because a solution with very high hydrogen ion concentration or hydroxide ion concentration is corrosive and harmful. For example, as shown in this figure, a pH less than 5 would affect fish reproduction, and a pH less than 4 will kill fish. So we can't discharge highly acidic or alkali solution directly into the environment. What we can do is to neutralize the solution first. If the solution is acidic, then we add a base. If the solution is basic, then we add an acid. The hydrogen ion concentration of the acid will combine with the hydroxide ion of the base to produce water, and a salt solution is produced in the meantime. Please read the lecture notes for more information on this slide. Now let's move on to the last topic of this presentation, acid dissociation constant. Acid in this phrase means weak acid, as strong acids can dissociate completely in water, and therefore equilibrium constant is generally not applicable to them. Again, the equation for acid dissociation constant can be derived from the general chemical reaction and the general equilibrium constant. I would like to mention again, the HA here is not the formula for any particular weak acid. It only denotes weak acids in general. The acid dissociation constant equation has the same structure as the general constant equation for self-ionization of water. The subscript A stands for acid. But for self-ionization of water, we can simplify the equation a little bit because the concentration of water in dilute solution is a constant, 55.56 mole per liter. But we can't simplify this acid dissociation constant equation, as the concentration of acid in water can be different much. For example, we can put 1 mole of acid into 1 liter water. We can put 2 mole in 1 liter water, or 0.001 mole in 1 liter water, and so on and so forth. So for acid dissociation constant, we cannot omit the denominator. The concentration of acid. Another point I would like to see is the acid dissociation constant of weak acid is usually very small and usually below 10 to the negative 3. So for such small numbers, we again prefer the log scale. So rather than seeing, for example, the acid dissociation constant of a weak acid is 7.2 times 10 to the minus 5, we can simply see the pKa here of this acid is 4.14. Remember, the little p means negative log. Please read the lecture notes for more explanation on pKa. This value be uploaded on Blackboard in revision folder for your practice. Finally, Another question for you. I have not got much chance to introduce the Le Chandelier's principle properly yet, although I suspect many of you are very familiar with this. Please read the information on slide 23 of lecture 8 and associated lecture notes thoroughly on this principle, and work out if the self-ionization of water is an isothermic or endothermic reaction according to the information provided in this table. So that's all for this lecture.